So this is your current. So inject the current there. Your meter should have this. And then another wires connecting the voltmeters. That's all. But of course, we need to observe the length. Make sure this one is X. And this one is D. And X is equal to 0.618 D. Okay. So the behavior of resistance. So this is resistance. This is your D. So X is here 0.618. In meter, in ohm. Now, your resistance, your correct resistance is this one. If you change D a bit, X a bit longer than 0.618, so this is X. This is X. If it's a bit longer, it will give a higher value. If it's shorter, it gives smaller value. So the resistance goes like this. You know, it goes larger than the true value if you make it longer, or it becomes smaller than the true value if you go smaller. But if the distance is too large, very large, like 100 meters, the difference here could be very small. Okay, if you make error. So the standard says you should make sure if you the changes, I think I can't remember the distance from the correct value. It should be like 2% change. If you move like 1 meter away, the change is 2%, less than 2%, then you're okay. So meaning to say, you need to make sure your D is large enough so that you have almost a flat curve. A flat curve like this. Okay. But if the distance D is too small with respect to this structure, which is, let's say, L here, the whole grounding has a certain dimension. If your distance is in similar dimension with your, if the D is similar with your electrode dimension, then you will have something like this. You know, very large change with changes in distance because you are too close. So if you make it very large, like 100 meters, whereas your electrode is about 10 meters, 10 times at least, then you have a good measurement with low uncertainty. So roughly we'll say L. Now, can you see the graph just now? Yes, okay. So I'm at the graph now. So D should be larger, about 10 times. Okay. Then you have accurate reading. You understand? But if you don't know, what is the length of your electrode, then it's okay. Just make D as large as possible. 100 meters usually we do it, or 50 meters at least. Okay.
Okay.
Agree.
Prof, I have one question I want to ask you.
Yes.
We do this the purpose of doing this is to get the raw of the soil, is it?
No, no, no. You see, this is to get the resistance of the electrode using fall of potential technique.
The
Remember?
resistance of the electrode.
Remember? See, we are actually resistance measurement. Can you see the slide now?
Okay.
So resistance measurement, you have electrode already buried in the soil, and you want to measure the resistance. So to measure the resistance of the electrode, you use what we call fall of potential method. So you don't know what is the electrode.
But we can get the resistance of the electrode by knowing the material of the electrode.
But we don't know.
And then we.
But we don't know. For example, customer asks you, can you measure my electrode resistance? I don't know what's inside. So this is how you do it. Okay? You don't know what's inside the soil.
Okay, another question is. Another question.
Yes.
The electrode itself has the resistance, right? And
yeah,
the soil itself also has their own resistance.
No, actually the concept is like this.
So when we design
the concept is when you bury some electrode, it will give you an equivalent resistance. For example, we've shown you last time, a vertical rod will give a certain formula. But this is if you know the dimension. If you know the dimension. Okay, this is an example of resistance for a grid. This is an example of resistance of a rod. This one, two rod, perpendicular, horizontal, and so on. So in the beginning, of course, you can design this, but over the time, row will change. You can see there's a row there. So to know exactly what is the resistance, you don't know the row also. You can measure row.
The row is the
soil
resistivity of the soil, right?
Yes, yes, yes. So,
but why don't we? But there is resistivity of the electrode itself also, right?
No. You must remember like this. When you insert an electrode into the soil, the electrode itself has some resistance, but this resistance is very small because the resistivity of copper, for example, is very, very small. So basically, it's a conductor. Basically, it's conductor. It doesn't have any resistance on its own.
Okay.
But when it is being put in the soil, when the current flows through it, we have what we call grounding resistance. Grounding resistance means the electrode inside the soil will give a resistance as seen by the current. You understand? It's like earth grounded conductor, and the ground is a bulk soil which has a resistivity rho, a large bulk of soil. It's not just surrounding it, but the whole soil. Yes.
Can we say like this? We just ignore the resistance of the electrode.
Yes, it's because it's very small comparatively. It's like less than 1 milliohm, whereas the resistance of the rod, resistance of the grounding rod means the rod inside the soil, is like 50 ohm or 100 ohms. So that's much bigger. Okay. Now, we have already shown you how to measure the resistance. So if you are in the field, you need to have what we call three electrode or 3 probe meter, 2 probe for the current, another 2 probe, shared 1 probe with the voltage for the voltage. Therefore, we have what we call a 3 probe meter or 3 electrode meter. If I can show you, of course, this electrode itself has some resistance, but this is minimum. But the resistance we are talking about is actually with the soil. See, the current will go all the way there. And all this will give an equivalent resistance. Okay, you can read now. V must be at least 10 times, already said to you. Another thing you need to consider, perpendicular direction. Okay, just now, you have electrode here, right? So you need to put your probe here, but you should also repeat perpendicularly. You understand? Why? The reason being, if you have a pipe in this direction, a metal pipe, then your reading will be affected because the current will flow bypassing the soil into the pipe. So if you do in another direction, the measurement like perpendicular direction, you do westward just now, now you do northward, then you can have, if you have a different reading, that means one of them is erroneous. Understand?
Yeah.
Okay. So you should at least repeat. If they are giving the same value, that means no buried conductors inside, no interference. And then I've already said to you, if you want to see your uncertainty is correct or not, you can change you can change X a bit smaller than 0.618 and a bit larger, and you should have less than 2% change. Then if you have less than 2% change, your reading is stable. Let's say you change 1 meter less, 1 meter higher, and then the reading still maintained within 2%. Then you have a correct D and X. You understand? This is related to number 1 there. At least 10 times.
Yeah.
Okay. Okay. There is one issue. If you use a DC power supply and therefore DC current, you will have what we call polarization. This polarization is due to you use DC current. So in our case, we don't use DC. Okay, we use some kind of pulse or impulse that doesn't ionize the soil, make plus and minus charges accumulate or polarize. So you should avoid this problem. Or you can use what we call a resonance system. Resonance system, you can use AC current for your injection current, but that frequency of the current is actually resonate the L and C of the grounding electrode. You remember the grounding electrode not only have R, but also series L and parallel C. But the L and C can be cancelled out if your current has a certain frequency, the same as the L and C resonant frequency. Then the L and C will cancel out. Your whole structure of RLC will be equivalent to R at resonating frequency. So you can have another system. Instead of DC, you use impulse, or you can use resonance system to make sure what you're measuring is pure R. Okay, if you have time, we can do measurement in the field, but at the same time, you should do this homework just to learn a little bit more about resonating techniques, as well as how to minimize the polarization effects.